Ribosomes, fatty acids, polyketides, non-ribosomal peptides, and polymeric carbohydrates all share a common property that they involve enzymes that perform multiple chemical reactions during each round of substrate binding. This poses challenges and opportunities for genetically encoding these biomolecules. Monofunctional enzymes make metabolic engineering relatively easy. These are the enzymes that bind to a substrate, do some chemistry, and then release the modified product. There are additional types of enzymes that similarly can be described by this model of substrate comes in, product comes out, but a large number of reactions take place when the enzyme is associated with the substrate. They operate like an assembly line. Thus, black boxing the internal function of the enzyme would hide all the interesting details. Without understanding how to manipulate the internal function of the enzyme, you could still refactor it for expression in another host, and in that sense it behaves like any other enzyme, and the reactions it performs should transfer from host to host. However, you can manipulate the function of biomolecules more deeply. For example, let's say you wanted to change the product to be different in just one region of the molecule. That will require digging into the sequence of the enzyme and changing the portions of the megasynthases that construct that region of the molecule. In this sense, it is an act of protein engineering, not just the usual device project. However, as we examine the inner workings of these megasyntheses, you'll see that they have a great deal of internal structure that allows us to approach their engineering in ways very similar to how we do pathways from monofunctional enzymes. You have already been introduced to one type of megasynthetase, the ribosome. It inputs amino acyl tRNAs in an mRNA and outputs a protein. Since the information about the sequence of the monomers in the protein are defined by the mRNA, you don't need to worry about modifying ribosomes to make a new protein. You simply create a gene that encodes the protein and the rest just happens. This will not be the case with the megasyntheses associated with secondary metabolism. Information about the final structure of the product is defined by the primary sequence of the synthase. So we need to understand what's going on inside these large biomolecules to engineer them.